So we will finish chapter 14 tonight. But let me ask before I start, are there any questions about anything? No. The final exam is posted. Craig, did you have a question?
I was just going to say, I'm sure I'll have questions after I take the final.
After the final, during the final. So the final exam is posted and available. It's due Monday evening, this coming Monday. So you can certainly do it beforehand. I may try to grade whatever comes in earlier than that, mostly because I think the turnaround for this is pretty quick. Like I need to have grades into IOSB. I have the date Thursday in my head, but I think I've had to have them done by Tuesday in the past, Tuesday or Wednesday. But we'll see. I'm sure there's a way I could look that up, but I'm not motivated enough to do it. So I'll cross that bridge when I get to it. So the only concept from tonight that actually shows up on the final is standing sound waves. And so I'll talk about that. And then there are two other concepts that I think are worthwhile talking about, particularly as they generalize to wave properties. We're talking about it in the context of sound, but they are general wave properties. And you will talk about light in 202, and light is a wave. Oddly enough, it's also a particle, but that's a physics 3 idea. Turns out particles are also waves. That's also a physics 3 idea. Just so you know, if you ever take a modern physics course, the bottom line for modern physics is everything you learn in physics 1 and physics 2 is only mostly right. Like our expression, let's say, for example, our expression for kinetic energy is half mv squared. That only works if you're not traveling really, really fast, right? If you approach the speed of light, that expression doesn't work anymore. It's the bottom line of special relativity. So if you're interested in that, take a modern physics course. Okay, so let's talk. Let me bring up my...
Can I ask a quick question?
Of course you can.
Are you willing to leave the videos for this class up until after physics 2 is over, in case we want to come back and look at some of the wave stuff? Or
yeah, sure.
Okay.
Yeah, I'll leave that.
I'm not sure how much of a tie there is, but I'd rather be able to know that I can come back and look at it than...
Yeah, that's no problem at all. I'll leave that up.
Thank you.
Okay. There. So the three things I want to talk about. Let's talk about standing sound waves. I started this last night, right? And then I posted the video about it. So here are some images for standing sound waves. This is like a graphic representation of what a standing sound wave in a tube looks like. I mentioned boomsticks last night. What I meant or what I was actually alluding to are boom whackers. I played that video into last night's video. Again, they're just like plastic tubes, and when you hit it, there's a tone, a distinguishable tone, right? A noticeable tone. There's also a percussive thwack to it, but particularly when you compare it to different lengths, you can hear that there are different tones. And so I found a group that plays music with those. I also posted a video of the Whirly tube, I think is what they're called. Again, this is just like a hose, right? Then if you swing the hose around, you can hear these resonant frequencies. And if you swing it slowly, so this is an open tube. So that would be like, yeah, sure, this guy. You swing it slowly, that's this guy. But if you swing it faster, you can access the higher harmonics, and you can actually hear these tones. Again, the major tone you hear is the fundamental, kind of like a guitar string, right? When you pluck a guitar string, what you hear is the fundamental frequency. You can cause higher harmonics to happen. Actually, the higher harmonics are happening. It's just they're quiet compared to the fundamental. But if you mute the string, right? So you pluck the string and then you put your finger close to it to like mute out basically if you put your finger close to the node of another harmonic, you'll mute out the fundamental, but not the higher harmonic. So you can get harmonics out of that. Okay, so an open tube, the pictures are literally the same as the pictures we drew for standing waves on a string. For a closed tube, I didn't label it here, but that's what I mean. For a closed tube, the waves look different, but they're literally the same number of waves in the tube for each mode. So the math is the same for both of those. An open closed tube, though, is a different critter, right? And you can see the waves for this look different. The fundamental is a quarter wave instead of a half wave, and so that lets you access lower frequencies for the same length of tube. So let's do an example for that. I did one example in the videos. Let's do another example. Scroll down a little bit. Not that one. Yeah, great. So, so here's an example, a pipe organ, right? So here's a specific pipe for this organ is made to play a low note, 27.5 hertz, which is pretty low. It's the same as the lowest note on the piano. Great. So assuming the speed of sound is 343 meters per second, what length of open tube is needed? And then if we used an open closed tube, what length of tube would be needed? All right, so we'll assume that we're accessing the fundamental frequency here. All right, so we're saying F1 is 27.5 hertz. We also know that the speed of sound, is 343. That's supposed to be a 4, I promise.
Are we supposed to be able to see your screen right now?
Yeah. Thank you for mentioning that. So the stuff I circled earlier didn't mean anything. You'd think this would happen more often. Just the last night. It was the last night. Do you have any experience teaching online? Oh, yeah. This is what I was trying to show you. My apologies. Thank you for letting me know. So this was the open and the closed. That was the math for it. And here's the open closed. Fine. Okay. So anyway, the bottom line is we have this set of equations, right? For wavelengths and frequencies. And so you get an infinite set of frequencies and wavelengths, right? Although you can't hear all of them because your ears are only sensitive to it. I mean, it's a pretty wide range, but it's not infinite. But largely what we hear is the fundamental. So that's what I'm suggesting here is not that, this one. Is here, example 6, right? So the pipe organ is made to play a low note. That's our frequency. We're given the speed. So we're looking for a length, right? And we're looking for a length for 2 setups, an open pipe length and an open closed pipe length. So let's do open first. What I know for an open system is that lambda sub n is 2L over n, right? I also have an expression for the frequencies, but let's just do wavelength. All right, so I have F1. I could use F1 and the speed to come up with lambda 1, right? Lambda 1 will be, if we were called it V equals lambda F, this is going to be V over F1, right? So that speed is 343 meters per second divided by the frequency is 27.5 hertz. Hertz. So what I get for that wavelength is 21.9 meters. No, that's not right. Look, that's the wrong problem. Did I do it that way? I didn't do it that way in this. That's fine. We'll do it that way. So 343 divided by 27.5 is 12.47 meters. Okay, so we're looking for length, and I know lambda 1. So lambda 1 equals 2L over 1. Right? And that lambda 1 is 12.47. So 12.47 meters equals 2L. So L is going to equal twice 12. So that's like 24. Nope, it's not twice. It's divided by. So it's like 6. Yeah. 6.24 meters. So that's for an open system. For an open closed system, lambda sub n is 4L over n, right? So we can see pretty quickly, instead of dividing by 2, I'm going to divide by 4, right? So we'll plug in one more line. 12.74 meters equals 4L divided by 1. So L is then 3 meters, 3.12 meters. Again, each of these systems would give you the same frequency. Now, the sound of the tone might be different, meaning the frequency is the same, but you know, you can listen to a trumpet and a flute play the same note, right? Literally exactly the same note, and they sound different. That's because there's more to sound than just the frequency. But if all you care about is the frequency, looks like you ought to build this pipe organ out of open closed tubes because you can use half as much tubing. Does that make sense?
Is it 12.47 or 12.74?
I don't know. 12.47.
Okay.
The rest of it ought to be right though, because I didn't do that math on the fly. I can though. Yeah, 6.24 and 3.12. Yeah. Oh, come on. Trying to write through eraser. 47. 47. Cool.
How do we know that n is 1 in that equation?
So I'm trying to decide whether to give a general rule, because as soon as I do, it's like, oh, well, actually, in this case, it's not. Kind of like when you pluck a guitar string, the major thing you hear is the fundamental frequency, meaning the n equals 1 frequency. It's the same thing for this pipe organ. We'll assume that it's built to give us the fundamental frequency, right? But just like the whirly tube, right? When you swing this thing around, the fundamental is actually pretty easy to get. The higher harmonics you can get if you go really fast, but they're a little airy, kind of intended. So the bottom line, if you're building a musical instrument, we'll assume that we're getting the fundamental frequency out of it. Okay. Trying to decide, I think that's all I want to say for standing sound waves. So I'd like to move on to interference. All right, so I introduced interference of sound waves. I showed some animations. I'm not going to go back through those, but I will just give interference here. So let's imagine that we have two speakers driven by the same source, right? So they have the same frequency coming out of them, and they're in phase. All right, they're in phase, meaning when one gives a peak, the other one's also giving a peak. So the idea is if they line up this way, right? Meaning the peak of one overlaps with the peak of the other at the same location, at some location in space, right? So these peaks line up here and these peaks line up here. Those will interfere constructively, right? So that's constructive interference. Constructive interference. So that's going to be louder, right? The other thing that you can do is have a peak overlap with a valley, and that's destructive. That would be quiet. All right. And so mathematically, you can figure out whether you're in a constructive or destructive situation by looking at the path length difference, which just means from the two sources, I decide what's the length to one source, what's the length to the other source, and you take the difference, right? If that difference is an integer number of wavelengths, then the peaks are going to line up again. If it's an integer plus a half, a peak is going to line up with a valley. So that's the difference between constructive and destructive. So that's these two equations. All right, and I did an example of this, but I think I'd like to do another one. And then maybe I'll show another animation. Okay, so let's do an example. Again, the crux of this is the path length difference needs to be a specific number in order for this to be constructive or destructive interference. And really, you only notice this for single frequency sound. So it's not like you're going to go turn on your speaker and hear this unless you're using the online tone generator that we used for lab. Okay, so let's do example number 10. So in your room, you listen to two identical speakers mounted on the wall, separated by 4.16 meters. They emit identical sounds of frequency 686 hertz. So you and your friend are in here. It's kind of creepy if you think about it. You and your friend are just in your room listening to this tone. What are you guys doing? Nothing. And that's the physics setup. So that's just the deal. Okay, so what does it say? You are sitting in a chair. The chair doesn't really matter, but you're sitting in a chair at a distance of 5 meters from the wall, and your friend is standing 2.8 meters to your right. So you are here. You are here. And your friend is up here. So that means this distance is 2.08 meters. This distance is 4.16 meters, which means your friend is standing right in front of this speaker, and that distance I think is 5 meters. Great. We're also told that the frequency being emitted here is 686 hertz. Will you hear constructive or destructive interference? By the way, it doesn't have to be one or the other. It could be in between, right? So the wording of this problem suggests that it's going to be constructive or destructive. And in fact, in this case, it will be. Pretty quickly, we can figure that out, and I'll show you why. So you are the same distance from each speaker, right? So as long as those speakers are emitting in phase, it's going to be constructive. Actually, for every single frequency, it'll be sorry, I said destructive, and constructive. It'll be constructive. Right? How do I know? So let's draw there. We could call this path 1. We call this path 2. Sometimes I'll call these D1 and D2. And for constructive interference, I need delta D to be an integer number of wavelengths. And for destructive interference, I need delta D to be in plus a half, or you could write it as in minus a half. So for both of these, in is an integer, and in can start at 0. All right, so delta D equals 0 means you're in the constructive case where n equals 0. Does that make sense? That's important here because here, path 1 minus path 2 is 0 for this case, for A, or U, right? Let me not draw it to that location. I need to draw it over here. All right, so I could say equals in lambda. Well, this is true if n equals 0. So clearly we're in a constructive case. You guys buy that? I didn't even have to use the wavelength for this. Okay. So that's kind of boring. Interesting, but boring. What about your friend? Well, your friend here, constructive or destructive interference. So now we're going to have to figure out an actual path length difference, right? So I need to know what these two paths are. So let me redraw this situation a little bigger. So there's our speakers, there's the friend, and the two paths are this. I've got, call this path 1. I'll call it D1 and D2. Well, D2, come on, D2 is 5 meters. D1, though, is the hypotenuse of a right triangle, right? And this distance right here is 4.16 meters. So D1, let's make it blue. Can you guys hear my kids upstairs, like beating the crap out of my floors? Because I can. So D1 equals, equal sign is pretty terrible. That hypotenuse, right? What is that? On this page. 1.5. Look at that. 1.50 meters. Okay, so what's delta D then? Delta D is 5 meters minus 1.5 meters, which is 3.5 meters. Okay. So that's the path length difference. That's delta D. It's the left-hand side of the equation. What we'd like to know is, am I satisfying one of these two equations? Right? So the other information that I need is I need lambda, right? What is lambda? Well, I can come up here, figure that out. I have a frequency, and I know the speed of sound is 343. So the wavelength is going to be V over frequency, which is 343 divided by 686, which looks like a half, right? Half of a meter. Okay. So I'll write that down here. Lambda equals a half of a meter. So now I can look at this and say, well, look, the path length difference is 3.5 meters. That's 7 wavelengths, right? Because if I multiply 0.5 meters by 7, I get 3.5 meters. So that means the path length difference is an integer number of wavelengths. So this is constructive. Let me write that out in math. So I'm saying delta D equals question mark times lambda, right? If that question mark is an integer, this is constructive. If that question mark ends in a 0.5, this is destructive. Do you guys see that from the math? Really though, I don't want you to be confused about this. Oh, looks like I already wrote down there. Okay, so how do I find question mark? Well, I divide lambda over. So question mark, let's just divide it and erase the lambda. Question mark must be 3.5 divided by 0.5. which is 7, right? Which means n equals 7. Or really, I'm satisfying delta D equals n times lambda for n equals 7. So this is constructive, right? So the answer is constructive. Here's the confusing thing about this. And again, I don't think I'm definitely not asking you to do this on the final exam. I don't even know. There may be homework problems that are extra credit that have this in it. But this pitfall is in my head, so I'm going to tell you. So you're looking for an integer or something that ends in a 0.5. I've got two numbers here that end in a 0.5. So you may have stopped at this point and said, well, look, it ends in a 0.5. This must be destructive. Or like here, this ends in a 0.5. This must be destructive. Or here, that's literally 0.5. This must be destructive. But what matters is the ratio of the path length difference and the wavelength. That was actually an integer, so this is constructive. Okay. Let me do one other thing with this. So let's find a completely different frequency where you both hear constructive interference. So I want a different frequency that is constructive. So now the nice thing about this setup is now I know I'm using this equation. Right? Except I don't know what lambda is. I don't even know what n is. But I'm looking for different lambdas. All right? I do know delta D because no one is moving. So delta D is still 3.5 meters equals n times lambda. What this gives me is a set of wavelengths. All right? So every wavelength for which lambda sub n is 3.5 meters divided by, not 7. 7 is one of them. It's the one we already knew. N is constructive. Right? Because every lambda sub n that is 3.5 divided by m in satisfies this equation. Okay, so that gives me a set of wavelengths. What about a set of frequencies? Well, I can use this equation and solve for frequency. Again, frequency is v over lambda. And if I'm plugging in lambda sub n, I'm getting f sub n. So that's 343 meters per second divided by 3.5 meters times n. And if you do that math, you get 228.7 hertz. 228.7 hertz times n. So we could round that up to 229. So that means the frequencies are 229, or n could be 2. That would be 457, 458. I'm gonna go 458. If n equals 3, I feel like I did something wrong. I'm almost positive I did something wrong. It didn't change the final answer. I think that 7 should have actually been a 3 because I think I used the wrong thing for delta D, but I absolutely used the wrong thing for delta D. It's fine. We'll just move forward. 686 hertz, which was our original frequency, and so on. So there are actually an infinite number of frequencies that work here. Right? You're not going to hear all of them, but they're an infinite set. Let me shift gears a little bit, because that example is a little convoluted. Let me go. Yeah, here's basically where I want to be. Not exactly here, though. I want to go to here. So these are great. You may end up using some of these for 202 labs. These are simulations of physics things. All right. So look, you can rub a balloon on a sweater without even leaving your home. I want to do that. Look at that. And then I can discharge it over here. Now can I? I can't discharge it. I'm just pushing charges away over there. Can I take all the negative charge? Look at that. Whoa. It's attracted to it, right? Because we separated. Okay. I could spend like hours on this website. But what I really want is sound and waves, not the Fourier transforms. We'll do this, wave interference. All right, so I showed this in the video. So I want to talk about it for a second. So we have two sources. Let's do two sound sources. And you can see when you turn one on, this is just a graphical representation of the compressions and rarefactions for sound. And when we turn two on, you can see that they interfere with each other, right? That's what we're describing mathematically, are these interferences. And so you see the areas that are maximally interfering and the areas that are not interfering as much, right? The little gray stripes, I don't think you'll see if I point it. It's freezing. There. The little gray stripes are the points that are quiet. You can do this with light as well. So here's our green laser pointer. Here's a second green laser pointer. So what I want to point out is this: if you put a screen at the end, so basically, if you shine these two at a wall, what you'll see are bright spots and dark spots. Just like if you had two speakers and you walked along that same wall, you would hear, it would get loud and then quiet and then loud and then quiet. So you will see this in physics 2 for interference of light. And we use this kind of, this property of light all the time for all sorts of applications. So I wanted to show that and show you this tool so you can, play with it. So you can change the color. That's fun. Okay. Questions about this, you guys? So let's do the very last thing, which is the Doppler effect. All right, so again, I posted a video about this, but I posted it a little late. I had it done and just got a late start on uploading. But this PDF, this handout is actually pretty useful in showing it. All right, so again, these are just wave fronts leaving a source, and if the source is moving, the wave fronts pile up in the direction of motion. So the person that the source is moving toward actually receives wave fronts more quickly, right? That is literally a description of, I've used the word literally way too much in this lecture. I'll just drop it. Say it. That is simply a description of frequency, higher frequency, and someone who is on the side that on the back side of this motion, right, where the source is moving away, is receiving peaks more slowly than they would, so that's a lower frequency. This is something you're familiar with, right? When a train passes by and honks its horn, you hear a high frequency while it's coming towards you and a low frequency when it's going away, right? And it changes very quickly as it passes you. The math to describe that is here. The effect of observer motion versus source motion is they show up a little differently. All right. In the example that I worked in the hand and the video, it had two things moving toward each other, right? So one submarine moving toward another submarine. The one submarine fires a ping, right, a sonar ping, and the other submarine receives it. And the motion of both submarines toward each other, they both act to increase the frequency, right? The motion of the source shows up in the denominator. I want my pen to work here. And the motion of the observer shows up in the numerator. I'm not going to derive that because I've got 2 minutes left in lecture. I did want to point out this, though. I had always had the intuition before I learned more about the Doppler effect. I'd always had the intuition that the distance that the thing was to you, right? So imagining a train, if the train is far off versus closer to me, it felt like that should affect the Doppler frequency, but it doesn't. If it's coming straight at you, now if you have a train coming straight at you, you have bigger problems than trying to decide how the Doppler effect is going to work. But if the train is coming straight at you, this equation is exactly true, right? There's no like lateral motion to worry about. And so this is single frequency. So if I were going to plot, no, come on, I just want to move the thing. If I were going to plot, I just need like white space. Not there, not there either. Fine. Just do this. Observed frequency as a function of time. While it's coming toward me, and show it. I drew axes, I promise. There. While it's coming toward me, so this would be F, the actual emitted frequency, it would be above this axis. And just as it passes me, it's going to flip back down here. All right, so this is F prime while it's coming toward me, and this is F prime when it's leaving. Which I think is interesting. You could use this kind of plot to decide whether it's actually coming towards you or away from you. So let me say this, because I've got negative 60 seconds to talk. Light does exactly the same thing. So if you look at, well, here, you can fire radio waves at a cloud and decide whether it's moving away from you or towards you, decide how fast it's going. The speed guns that cops use, same principle, right? It fires light at you that bounces off of you, goes back to the source and is shifted because you're moving toward or away from. The amount of shift tells the device how fast you're going. We use the same thing for distant stars, right? So we can look at the spectrum for distant stars and see how far it's shifted from what we expect. So we know the spectral fingerprints of different molecules, so we know where those fingerprints should be. And what we notice is from distant galaxies, it's shifted toward the red. So they're lower frequencies, which means they're going away from us. And everywhere we look in the sky, everything is red shifted. That's how we know that the universe is expanding. All right, so, you know, sit on that for a little while. So I will ask one final time. You guys have any questions? Okay. Cool. So thank you guys for being in this course and for coming to lecture. And shoot me an email if you have any questions. Otherwise, you know, I'll see you later. Maybe around town. You know, if I'm wearing a mask, my beard pokes out underneath, so you'll know it's me by the no hair here and the hair down here. Yeah, I'll also be helping with discussions in 202. So if you're moving on to 202, maybe I'll see you in discussions. So have a great evening and a great rest of your summer. Bye, guys.
Thank you.
You bet.
Thank you.
Thank you.